Welcome to our quantum deep dive.
Hello.
Today we are plunging into a really fascinating corner of theoretical physics. We're going to explore a set of hypothetical particles that could, well, fundamentally change how we understand the universe.
Yeah, these particles, they're called squarks. And they aren't just, abstract ideas pulled out of thin air. They're actually a core prediction of a major theoretical framework.
And the search for them is happening, right now, at the absolute frontier of high-energy physics.
That's right.
Our guide for this deep dive is a really intriguing essay by Jörg O. Schneeppet. So our mission today is basically to unpack this source, figure out what squarks are, why physicists are so convinced they might actually be out there, and where the hunt for them stands.
It's intense, bro.
Oh, incredibly intense and challenging.
Think of this as your shortcut, maybe, to getting well-informed on a genuinely cutting-edge topic in physics.
Yeah, let's dive in. Okay, let's start with the big picture then. Why would physicists even, propose a whole new set of particles? What puzzles are they actually trying to solve here?
Well, there are a couple of really significant, challenging, big questions in modern physics that our current best model, the standard model, it doesn't fully explain.
Right.
One of the most pressing, probably the most famous one, is often called the hierarchy problem.
Ah, the hierarchy problem. That's the mystery surrounding the Higgs boson's mass, isn't it? Can you unpack that a little bit for us?
Exactly. So the Higgs boson's mass, the particle discovered back in 2012, it seems, surprisingly light, almost unnaturally light compared to what our theoretical calculations suggest it should be.
How so?
Well, quantum effects from all the other known particles, they interact with the Higgs, and these interactions tend to push its mass up dramatically towards incredibly high energy scales, like the Planck scale.
Right. It's like trying to keep, what was the analogy? A beach ball underwater. There's this huge upward pressure.
Precisely. A massive upward pressure. And to keep the Higgs mass where we actually measure it, the standard model requires this incredibly precise, seemingly unnatural cancellation. Like you need a downward force that matches the upward one to, parts per quadrillion or something. It looks like a bizarre cosmic coincidence.
Which physicists generally don't like. Coincidences, I mean.
They tend to look for deeper explanations, yeah. And that's where a theory called supersymmetry, or SUSY for short, comes onto the scene. SUSY is basically an extension of quantum field theory.
Okay, quantum field theory, or QFT, that's the fundamental framework, right? The mathematical language physicists use to describe all the particles and forces we know about.
That's the one. It describes particles as essentially ripples or excitations in fundamental fields that permeate the universe. Think of these fields and how they interact. There's some pretty complex mathematics behind it, like Lagrangians describing the dynamics.
And supersymmetry takes that framework and adds something new.
It extends it by proposing this deep underlying symmetry, a symmetry between the two fundamental types of particles we know. Fermions, which have half-integer spin like electrons and quarks, the stuff matter is made of, and bosons, which have integer spin like photons, the particles that carry forces, and the Higgs boson itself.
A symmetry between matter particles and force carriers. That sounds profound.
It is. And because of this proposed symmetry, supersymmetry predicts that every known particle should have a kind of shadow partner, a superpartner particle.
Ah, so it basically doubles the number of particles.
Pretty much. It doubles the particle zoo. So the familiar quarks get supersymmetric partners called squarks.
Squarks. There.
Leptons, like electrons, they get leptons. The gluon, which carries the strong force, gets the gluino. The photon gets the photino, and so on.
Which brings us squarely to the squarks themselves. The name kind of gives it away, doesn't it?
It does, yeah. Squark is just a mashup of supersymmetry and quark.
And the key difference between a quark and its squark partner is?
It's that fundamental property we mentioned, spin. While quarks are fermions, they have spin 12. The proposed squark partners are predicted to be bosons with spin 0. This predicted fermion-boson symmetry is really the absolute core idea of supersymmetry.
Okay, so they're theoretical partners to quarks, but they have 0 spin instead of spin 12. How does that help with that Higgs mass problem, the hierarchy problem you mentioned earlier?
This is where SUSY gets really elegant, theoretically speaking. Supersymmetry predicts that those huge quantum corrections pushing the Higgs mass up, the ones coming from regular particles like, say, the top quark.
Right, the beach ball pushing up.
Exactly. Those are almost perfectly canceled out by opposite corrections coming from their superpartners, the squarks in this case, the stop squark.
So the squarks provide the downward push.
Precisely. It's like the squarks naturally provide that perfectly balanced downward force on the beach ball. This stabilizes the Higgs mass without needing that awkward, fine-tuned cancellation that looks so unnatural in the standard model alone. This cancellation mechanism is one of the biggest, perhaps the biggest, theoretical motivations for believing squarks, and SUSY in general, might be real.
Okay, solving the hierarchy problem is obviously a huge deal. What else does supersymmetry and, by extension, Squarks bring to the table? Any other puzzles it helps with?
Well, another really compelling aspect, and the source highlights this too, is that supersymmetry helps the fundamental forces seem to unify.
Unify, you mean like the strong force, the weak force, the electromagnetic force?
Exactly.
Yeah.
When you calculate how the strengths of these forces change with energy, in the standard model they get closer at high energies, but they don't quite meet at a single point. But if you add the effects of all the supersymmetric particles, like squarks and gluinos, into the calculation, the running of these coupling strengths changes just enough so they converge much more neatly, almost perfectly, at extremely high energies.
Wow. Suggesting that maybe way back in the early universe or at some fundamental level, these forces were actually just different aspects of a single unified force.
That's the idea. Supersymmetry makes that concept of a grand unified theory, or GUT, look much more plausible mathematically.
Okay. Hierarchy problem solved, force unification supported. Anything else?
Yes, there's the massive mystery of dark matter.
Ah, the invisible stuff that makes up most of the matter in the universe.
The very same. We know it's there from its gravitational effects, but it doesn't seem to interact with light, so we can't see it. SUSY offers a natural candidate for this.
How so?
In many SUSY models, the lightest supersymmetric particle, the LSP, is predicted to be stable. It doesn't decay. And it often turns out to be electrically neutral and interact very weakly with normal matter. A particle called the neutralino is a common candidate.
Stable, neutral, weakly interacting. That sounds a lot like what we expect for dark matter.
Exactly. It's a perfect fit, theoretically. A WIMP, a weakly interacting massive particle.
And how do squarks connect to this dark matter picture?
Well, the heavier superpartners, including squarks, aren't expected to be stable. If they're produced, say, in the early universe or in a particle collider, they would decay very quickly.
Okay.
And their decay chains often end with the LSP. So squarks could decay into quarks plus the LSP, or other combinations. This means squarks produced in the very hot, dense early universe could have decayed, leaving behind a relic population of these stable LSPs.
Which could be the dark matter we detect gravitationally today.
Precisely. Squarks could have played a crucial role in setting the abundance of dark matter in the cosmos. For instance, a process like a quark and an anti-squark annihilating into an LSP and something else like $+ tilde to 1 plus X symbol could have been important.
So just to recap, squarks are these hypothetical partners to quarks, spin zero bosons, predicted by supersymmetry. They could solve the Higgs mass problem, help unify forces, and provide a pathway to producing dark matter. That's quite a portfolio.
It really is. That's why theorists have been so captivated by SUSY for decades.
Okay, let's get a bit more specific then. What else do we know about squarks, theoretically speaking? What are their predicted properties?
Right. So we've mentioned spin zero. Their electric charge is predicted to be exactly the same as their corresponding quark partner. So an up-squark would have charge +23, a down-squark on X of 13, just like up and down quarks.
So they carry the same electric label, if you will.
Exactly. They also carry color charge.
Meaning they interact via the strong nuclear force, the force that holds quarks together inside protons and neutrons.
Yes, just like quarks. This is important because it means they can be produced strongly in proton-proton collisions, like at the LHC.
Makes sense. And flavors. Do they mirror the quark flavors?
They do. There should be 6 squark flavors, corresponding to the 6 quark flavors. Up, down, strange, charm, bottom, and top squarks. Usually denoted with a tilde, like tilde, 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 tilde,
right.
tilde. The source also mentioned left-handed and right-handed variants. What's that about?
Yes. Chirality. It's a quantum mechanical property related to how a particle's spin aligns with its direction of motion. Quarks come in left-handed and right-handed versions, which interact slightly differently, especially with the weak force.
Okay.
Supersymmetry predicts that squarks inherit this, so you'd actually have a left squark and a right squark for each flavor. These can sometimes mix together to form the actual mass states we might observe, but fundamentally there are these two types.
Interesting detail. Now, the big one, mass, are they light like quarks or?
No, definitely not. If they had the same mass as quarks, we would have found them ages ago. They are expected to be significantly heavier.
How heavy are we talking? Well, that's the $1 million question, or maybe trillion electron volt question. The predictions vary wildly, depending on the specific CY model, and crucially, on how supersymmetry is broken.
Broken. What do you mean broken?
Well, clearly, supersymmetry isn't an exact symmetry in our world. Otherwise, the squark would have the same mass as the quark, the selectron the same mass as the electron. We don't see that. So the symmetry must be broken somehow, meaning the superpartners gain extra mass. How this breaking happens determines how heavy the squarks are.
So the theory doesn't give one precise number.
No, it gives ranges, often very wide ranges. Generally, people have been searching in the range from hundreds of GeV, that's giga-electron volts, hundreds of times the proton mass, up to several TeV, tera-electron volts, or thousands of times the proton mass.
And stability. Would we see them directly?
Almost certainly not. They're expected to be very unstable and decay incredibly quickly, typically in fractions of a second, long before they could reach a detector.
Decaying
Into standard model particles, like quarks or WZ bosons, and crucially, often into other supersymmetric particles, cascading down until they reach the lightest supersymmetric particle, the LSP.
That potential dark matter particle.
Exactly. That LSP, being stable and invisible to the detectors, is key to how we actually look for squarks.
Okay, the theory sounds really compelling, lots of elegant solutions, but theory needs proof. Where do we actually look for something like a squark?
The main hunting ground, as we've touched on, is high-energy particle accelerators. And the undisputed champion right now is the Large Hadron Collider, the LHC, at CERN near Geneva.
Right, the giant underground ring. And the experiments there, ATLA and CMS.
Those are the two big general-purpose experiments. Huge, incredibly complex detectors built around the points where beams of protons collide. They're specifically designed, among other things, to search for new, heavy particles predicted by theories like supersymmetry, including squarks.
And the basic strategy is just smash protons together really, really hard and see what comes out.
That's the essence of it. They accelerate protons to almost the speed of light, giving them enormous energy, and then collide them head-on. According to Einstein's EMC-VAT, that collision energy can be converted into mass, potentially creating new, heavy particles that weren't there before, like squarks.
So if a squark pair is created in a collision, what does the detector actually see? What are the signs they look for in all that debris?
Okay, there are a few key signatures. Since squarks carry color charge, they interact strongly. This means their production and the subsequent decay of their products often results in collimated sprays of particles called jets. High-energy jets are a common sign.
Jets of particles flying out. Okay.
But perhaps the most crucial signature, especially if ECSY explains dark matter, is missing transverse energy, often written as URT text miss.
Missing energy. You mentioned this before. That sounds counterintuitive. How can energy be missing?
It's not truly missing, of course. Energy and momentum are always conserved. But remember the LSP, the potential dark matter particle.
Yeah, stable and invisible to the detector.
Exactly. It interacts so weakly, it just flies right out of the detector without leaving a trace. So if squarks are produced, maybe a pair of them, and they each decay into something visible, like a quark, which makes a jet, plus an invisible LSP.
Ah, the LSPs carry away energy and momentum, but the detector doesn't see them.
Precisely. The detectors are designed to measure the energy and momentum of all the visible particles flying out, perpendicular to the beam direction. That's the transverse part. If the total measured transverse momentum doesn't add up to zero, it means something invisible must have carried momentum away.
It's like seeing the recoil but not the bullet.
That's a great analogy. That measured imbalance, that missing transverse momentum or energy, is a critical hint that maybe invisible particles like LSPs were produced.
So they look for events with high energy jets plus significant missing transverse energy.
That's one of the classic search channels, yes. There are variations depending on what the squarks decay into, but jets plus AT Texmus is a benchmark signature.
Okay, so the experiments have been running for years, smashing protons, looking for jets, and missing energy. What's the verdict? Have they found squarks?
The short answer, unfortunately, is no. Despite years of searching at the LHC by both ATLS and CMS, and analyzing truly massive amounts of data, no direct, unambiguous evidence for squarks has been found. Yet.
Ah, the big yet. That's always the key word in particle physics, isn't it? But surely the lack of discovery tells us something important.
It absolutely does. It's not just a null result. The experiments use the fact that they haven't seen these signatures to set limits. They can say, if squarks existed with a mass below X, we should have produced enough of them and seen a signal above the background noise by now.
So they're ruling out possibilities, pushing
Yeah.
the boundaries.
Exactly. They set exclusion limits. They can say squarks below a certain mass are now excluded with a high degree of confidence.
And what kind of mass limits are we talking about now? Are they getting serious?
Oh yes, the limits are quite stringent now and depend on the specific type of squark and what it decays into. But the source mentions, for example, that the lighter squarks, the partners of the up-down strange charm quarks, are generally excluded for masses below about 2.2 TeV, that's tera electron volts.
2,200 times the mass of a proton, roughly. That's heavy.
Very heavy. The partners of the heavier quarks, like the top squark, or stop, and bottom squark, which are theoretically very interesting for the Higgs problem, also have strong limits. Stops are often excluded up to around 1.3 TeV, bottoms up to maybe 1.5 TeV, again depending heavily on the assumed decay modes.
So if squarks exist, they must be hiding at even higher masses than we've been able to thoroughly probe so far.
That seems to be the implication of the current data, yes. Or perhaps they decay in ways that are harder to detect than the simplest scenarios.
Searching for these rare signals, these few potential squark events buried in, billions or trillions of other collisions must be incredibly difficult.
It's phenomenally challenging. One of the biggest hurdles is distinguishing a potential new physics signal, like squark production, from background processes. These are mundane, known processes predicted by the standard model that happen vastly more often and can sometimes mimic the signal you're looking for.
What kind of background processes?
For squark searches, common backgrounds include producing pairs of top quarks, which decay into jets and sometimes neutrinos, which cause missing energy, or producing W or Z bosons, along with multiple jets that can also look very similar. Teasing out a potential small signal from this huge sea of background requires incredibly sophisticated analysis techniques, detector calibration, and theoretical modeling of the backgrounds.
So just to circle back, they're hard to find. They haven't shown up yet within the current energy reach and data limits, but the theoretical reasons, the hierarchy problem, force unification, dark matter, are still incredibly compelling. Let's just quickly revisit why finding them would be such a massive discovery.
Right. Finding squarks would be revolutionary. First, it would provide powerful experimental evidence for supersymmetry. It would mean that underlying fermion-boson symmetry is real.
And it would validate that beautiful cancellation mechanism that explains why the Higgs boson isn't astronomically heavy.
Exactly. Solving the hierarchy problem naturally would be a huge triumph for SUSY.
It would also strengthen the case for grand unification, right? Showing that the forces really do seem to merge at high energies when you include the superpartners.
Correct. It would make the picture of fundamental forces much cleaner and more unified.
And critically, it connects directly to dark matter. If squarks are found and they decay into a stable, invisible LSP like the neutrino,
then we'd have essentially found the source of cosmic dark matter, or at least a major component of it. We'd understand what constitutes the vast majority of matter in the universe. That would be monumental, connecting particle physics directly to cosmology.
Okay. Monumental implications. But they haven't been found yet. Where does the search go from here? What are the challenges and future prospects?
Well, the lack of discovery poses significant theoretical challenges. If SUSY is real, why are the superpartners so heavy? Why haven't we seen them? It forces theorists to reconsider the simplest SUSY models, explore more complex scenarios for how SUSY is broken, or even ask if maybe SUSY isn't the answer to the hierarchy problem after all.
And experimentally, what's the main hurdle now?
The primary experimental challenge is simply energy and luminosity. If squarks are significantly heavier, say up around 3 TeV or even higher, the current LHC might not have enough raw energy to produce them in large enough numbers to be clearly distinguished from the background.
So we need more powerful machines.
Essentially, yes.
Yeah.
Or more data from the current ones. The immediate future involves upgrades to the LHC itself. The high luminosity LHC, HL-LHC, is planned to start operating later this decade. It won't increase the collision energy much, but it will dramatically increase the rate of collisions, the luminosity.
More collisions means more chances to see rare events.
Exactly. More data gives you better sensitivity to potentially very rare signals, or helps you probe higher masses. Beyond the HL-LHC, physicists are actively planning for potential future colliders.
Like what?
There are proposals, like the Future Circular Collider, FCC, at CERN, envisioned as a 100-kilometer ring capable of reaching collision energies around 100 PeV, a huge leap. There are also ideas for high-energy muon colliders. These future machines are explicitly designed to push the energy frontier far beyond the LHC, allowing us to search for particles like squarks at much higher mass scales.
So the hunt continues, pushing to higher energies and more data. Are there other ways to look besides colliders?
Yes, absolutely. As we mentioned, the connection to dark matter is key. Dedicated dark matter detection experiments deep underground trying to catch LSPs hitting atomic nuclei, or telescopes looking for signs of LSP annihilation in space could potentially find the LSP directly.
Which would be indirect, but very strong evidence for SUSY and Squarks existing at some higher mass scale.
Exactly. It's a multi-pronged approach.
Sure.
Colliders search directly by trying to produce them, while dark matter experiments search indirectly by looking for the lightest, stable end product.
The stakes here just seem incredibly high, driving all this effort.
They truly are. Finding Squarks, finding any evidence of supersymmetry, would fundamentally rewrite our understanding of particle physics. It would confirm this beautiful, deep symmetry of nature and solve some of the biggest puzzles we face.
But not finding them, even with the HLLHC, even with future colliders.
Well, that would be just as profound in a different way.
Oh.
It would force physicists to seriously reevaluate. If SUSY isn't the answer to the hierarchy problem, what is? It might mean we need completely new theoretical frameworks, perhaps involving extra spatial dimensions or something even more exotic we haven't thought of yet. It would signal that nature is perhaps more complex or just different than our most elegant theories predicted.
A genuine fork in the road for fundamental physics.
Absolutely. Either way, discovery or continued absence, the search for Squarks is pushing us towards a deeper understanding of reality.
And that really brings us towards the end of our deep dive today. We've journeyed through the core ideas in Yorgo Schneppat's essay, really exploring these hypothetical particles, the Squarks.
Yeah, the theorized supersymmetric partners of quarks. We've looked at why physics predicts they might exist, tackling big issues like the hierarchy problem, force unification, and potentially explaining dark matter via the LSP.
We've explored their predicted properties spin zero, same charges as quarks, but much heavier, and how experiments, particularly ATLA and CMS at the LHC, are desperately hunting for them using telltale signs like high-energy jets and, crucially, that missing transverse energy signature.
And we've touched on the profound implications their discovery would have, essentially validating supersymmetry, versus the deep questions raised by their continued absence so far.
Yeah, despite that strong theoretical motivation and these incredible extensive searches pushing the boundaries of our technology, Squarks remain elusive. They're pushing the limits, forcing theorists and experimentalists to refine their models and search strategies.
Which leaves us, and you, with a really provocative thought to mull over, drawing from Schneppat's work and the current state of physics. Will the next generation of experiments, the HLLHC, or maybe a future 100 TV collider, finally pull back the curtain and reveal these supersymmetric partners, confirming this elegant layer of reality?
Or will their continued absence force physics down a completely different path into potentially uncharted theoretical territory to explain the fundamental workings of the universe? It's a genuinely thrilling, uncertain, and absolutely critical time for fundamental physics.
Couldn't agree more.
Thank you for joining us for this deep dive.
Thanks for listening.